Hi there and welcome to tutorial 5 on approximating the normal. This is for the Edexcel S2 A-level module and is a crash course towards the exam. So if you're looking for further help with your studies, do check out youtube.com/Mr. Arnold's Maths or follow me at Mr. Arnold's Maths on Twitter. Okay, so this tutorial is going to be all based around approximating binomial and Poisson distributions using normal approximations. So I'm going to start off with a nice question here that just kind of gives a brief recap of all three. So we've got three random variables, r, s, and t. They're distributed as follows. So r is binomially distributed with 15 trials and a probability of success being 0.3. S is a Poisson distribution with parameter 7.5, and t is normally distributed with a mean of 8 and a standard deviation of 2. So the first part is to work out the probability that r equals 5. R is a binomial distribution, which means I'm going to use the formula in this case. So the formula gives me 15 choose 5 times 0.3 to the power of 5 by 0.7 to the power of n minus x, which is going to be 10. And then when we plug that into the calculator, we're going to get 0.206. So a nice handy 2 marks. S, we want the probability that S is 5. Well, S has a Poisson distribution. The rate is 7.5, or the parameter is 7.5, or lambda is 7.5. So let's swap over colours here. Probability that S equals 5. Again, we're going to have to use a formula. So it's going to be E to the minus lambda, E to the minus 7.5, times lambda, which is 7.5, to the power of X, which is 5, all over X factorial, which is going to be 5 factorial. And when we plug that into our calculator, we get 0.1094. Finally, probability that t equals 5. This is a normally distributed random variable. These two are both discrete random variables, which meant that they have particular values, probabilities at particular values, but because this is continuous, the probability that t equals 5 must be equal to 0, because this is a continuous distribution, which means we must have a range because we're looking for areas under curves, and the probability that t equals 5, well, that's just the area of a straight line, which is going to be equal to 0. Okay, let's have a look at some characteristics. So we know that the binomial and the Poisson are discrete distributions. The normal is a continuous distribution. So what does that mean for the binomial and the Poisson? Well, essentially it means that the probability that x is less than or equal to, say, 2 is not going to be the same as the probability that x is less than 2. The reason being that the probability that it's less than 2 is going to be the same as the probability that's less than or equal to 1. And that's because it's discrete. However, with a continuous random variable, the probability that x is less than 2 is going to be exactly the same as the probability that x is less than 2, because x equal to 2 is going to be 0. Okay? Now, so if we think about it from this point of view, suppose I was asked the probability that x is equal to 3 to the nearest integer, I would have to apply a continuity correction, which I'll talk about in a moment, because I can't have a particular value using continuous distributions. But if it was to the nearest integer, that means it could have been as low as 2.5 or as high as 3.5, but not including the 3.5. So basically we're just thinking, what are the upper and lower bounds if I round it to the nearest integer here? Okay, suppose the probability that x is less than or equal to 5 is what I'm trying to do, and I'm using a normal approximation. We have to apply what's called a continuity correction here. So because I'm looking to the left of 5, but I must include the 5, well, that means that the probability that x is less than or equal to 5, when I apply the continuity correction, is roughly the same, that it's less than or equal to 5.5. It could have been as much as 5.5. X greater than 4, I'm looking to the right of 4, and I'm not allowed to include 4. That means x must be greater than or equal to 4.5. What about between 17 and 20 inclusive? Well, that is going to be, I could have been as low as 16.5. and could have been as high because it includes the 20, 20.5. And what about between 3 and 7? Well, that's going to be, well, I must include the 3, so it could have been as low as 2.5. I don't want to include the 7. That means at most it could have been 6.5. At most we want to go up to 6.5. Okay, let's have a look at some examples here. So if I want to approximate a binomial, if n is large and p is close to 5, what we can say is my binomial can be approximated by a normal distribution such that the mean is np and the variance is np times 1 minus np, the variance or sigma squared. So, this is from June '06, it's question 5. A manufacturer produces large quantities of coloured mugs. It's known from previous records that 6% of the production will be green. A random sample of 10 mugs was taken from the production line. A. Define a suitable distribution to model the number of green mugs in this sample. Well, we're taking out a selection of mugs, so there's a number of trials, and I want to know are they green or not. So we have a success. So I'm going to say let x be the random variable green mug. That means x has a binomial distribution. The number of trials is 10 because we're taking a sample of 10, and the probability of success is going to be 0.06. So as part A, find the probability that there were exactly 3 green mugs in the sample. So in other words, I want the probability that x is equal to 3. And we're going to use the formula here. So there's 10, n is 10, choose 3 times the probability of success, 0.06, to the power of x, which is 3, by the probability of failure, 0.94, to the power of n minus x, which is going to be to the power of 7. And when we plug that into our calculator, we're going to get a value of 0.168. 0.0168, should I say. And that's part B. Okay, a random sample of 125 mugs was taken. Notice that n has become large now. Find the probability that there were between 10 and 13 inclusive green mugs in the sample, first of all using a Poisson and then a normal approximation. Okay, so between 10 and 13, so we're looking for the probability that is between 10 and 13 inclusive. Okay, and we're going to approximate first of all using a binomial. Right, well, let's do part 1 here. If x has a binomial distribution with 125 is the value of n and 0.06 is the value of p, well, that is like modeling a random variable y that has a Poisson distribution with parameter 7.5. 7.5. Now, just so you know where the 7.5 came from, when we're approximating a binomial using a Poisson, that is when lambda equals np. Right, so y is a Poisson distribution with parameter 7.5. Okay, so we're looking for the probability that 10 is less than or equal to y, which is less than or equal to 13, which is going to be equal to the probability that y is less than or equal to 13, subtract the probability that y is less than or equal to 9. And that's because this is a discrete random variable and a discrete distribution. Okay, so I'm going to use the tables to look this up such that the lambda is 7.5 and we're looking for less than or equal to 13. When I do that, I get 0.9784, and I'm going to take away 0.7764. And when we put that into our calculator, we're going to get 0.202. So that's part 1 done for 3 marks. Part 2 for 6 marks. Let's change colours again. Part 2. Right, so we're going to approximate using a normal here. And if we remember, I can approximate the normal when mu equals np and sigma squared equals np times 1 minus p. So mu is np, so in this case mu is going to be 7.5, and sigma squared, when we plug this in, we're going to get 7.05. That's the first part done. So what we can say is, let's call it T has a normal distribution with mean 7.5 and variance of 7.05. Okay, and what we want to do is we want the probability that x is between 10 and 13 inclusive. Now, because we're going from discrete to a continuous distribution, what we need to do is apply the continuity correction. So this x could have gone as low as 9.5, and because we're including 13, it could have been at most 13.5. So we're going to work out this probability. Now the next thing that we need to do is to standardize. So I need to standardize this, which is going to be equal to the probability, and you do to standardize, you do the particular value minus the mean over the standard deviation. So we're going to do 9.5 minus the mean mu, which is 7.5, over the standard deviation, which is going to be the square root of 7.05. And that's got to be less than or equal to z, because now we're going to the standardized normal. And then standardizing 13.5, we get 13.5 minus the mean, which is 7.5, over the standard deviation, which is square root of 7.05. Okay, so bashing those into the calculator, and we're going to get values of 0.75 less than or equal to z, less than or equal to 2.26. Okay, let's make a little bit more room here. So z is between 0.75 and 2.26. So I'm going to sketch a little diagram here because it's the first question on the normal distribution you may have seen in a while. So we have our axis. I have a feeling this is going to look terrible, but could be worse. Right, so it's between 0.75 and 2.26. Right, remember that the mean is 0 in the standardized normal, so that means 0.75 is going to be, say, over here, so call that 0.75, and 2.26, say, is up here somewhere, 2.26, and we want the probability that it's in here. So if we think about this carefully, we can use the standard normal tables to work out the probability that it's less than 2.26, which would be everything. I'm going to shade this in blue. So the probability that z is less than or equal to 2.26 is going to be in blue, which is going to be everything. So we've got everything in here, and what I'm going to do is I'm going to take away the probability that z is less than or equal to 0.75, which is going to be everything in the green, And if you, hopefully you can see that if I take the blue part away from the green part, I get left with the region we're looking for, this region in here. So the probability, let's go back to black here. The probability that z is less than or equal to 2.26 using the tables is 0.9881, and the probability that z is less than 0.75 is 0.7734. And when we put that into the calculator, we're going to get 0.2147. Okay, let's move on. What about Poisson approximation? So, all we've got to remember is that if x has a Poisson distribution with parameter lambda, well, remember the mean is lambda and the standard deviation is, the variance is also lambda. That means y can be approximated by normal distribution with mean lambda um, and variance lambda. Now, that is when it tends to work when lambda is bigger than 5. So as long as lambda is bigger than 5, it tends to work. We want large lambda. Okay, let's have a look at an exam question here from June 09, question 5. We got an administrator making errors in her typing randomly at a rate of 3 errors every 1,000 words. And we're asked here that in a document of 2,000 words, find the probability that the administrator makes 4 or more errors. Okay, so if it's 3 errors every 1,000 words, well, in 2,000 words, we would have 6 errors. So it's going to be a Poisson distribution because we've got a rate. So we can say x has a Poisson distribution with parameter 6. We want the probability that the administrator makes 4 or more errors. So if x is the random variable that an error is made, we want the probability that x is greater than 4 or more, greater than or equal to 4. Right, well, we should remember that that is going to be the same as 1 minus the probability that x is less than or equal to 3. And what we can do is we can look the probability that x is less than or equal to 3 up in the tables, and we get 0.1512. And when we work that out on the calculator, we get 0.8488. So, quite handy there for 3 marks. Next part, it says the administrator is given an 8,000 word report to type, and she is told that the report will only be accepted if there are 20 or fewer errors. Use a suitable approximation to calculate the probability that the report is accepted. So if it's 8,000 words and we do 3 every 1,000, that means lambda is going to be equal to 8 times 3, which is going to be 24. So we have our we want to know the probability that x is going to be at 20. The report will only be accepted if there are 20 or fewer errors. So essentially what we want to work out is we want the probability that x is less than or equal to 20. So 20 or fewer errors. And also x has a Poisson distribution with a parameter 24, and we can see that lambda is quite big here, and we're using an approximation. That means we can use the normal distribution. So what we're going to do here is this is going to be approximately equal to say y, which has a normal distribution, parameter 24 and 24. And what we're going to do is apply the continuity correction to this. So this is going to be approximately equal to the probability that y less than or equal to 20, which means I'm looking to the left of 20. I can include the 20. That means at most it could have been 20.5. Okay, so what we're going to do is we're going to standardize this now. So that's the probability that y, so I'm just so you know, I'm standardizing this here. not y, let's change it, changes to z now because we're going to the standard normal. Z is going to be less than or equal to x, or the particular value 20.5, minus mu 24 divided by the square root of 24, which is equal to the probability that z is less than or equal to, and putting that into the calculator, minus 0.7144. 7144. Okay, so what we're going to need to do is actually sketch this out as well. So you get to see another one of my wonderful diagrams here. Or I could probably try and copy one over, but however, we'll try and give it a go. Okay, so I'm just going to sketch a diagram here to show roughly what we're thinking about. Remember, the mean is mu is 0 in the standard normal, and minus 0.7144 is going to be, say, over here somewhere. Minus 0.7144. I want that region there, and we can use the symmetry. If that, say, was 0.7144 and I do 1 take away this, which would be all of that, it's going to leave me with this green region, and this green region in here should be the same size as this red region. So what we're going to do is we're going to do 1 minus the probability that z is less than or equal to 0.7144, which is equal to 1 minus, and looking this up in the table, we get 0.7611. And then when we work that out, we get 0.2389. Okay, and that concludes my video on approximating the normal. So there's not really a whole lot in it. The key things to remember is the continuity correction, and if you're in doubt about how to kind of work out your normal distribution values, do check out my old videos from the S1 course on the normal distribution. All will be made clear there. Okay, thanks for watching. Hopefully you found it useful. I'll be back again soon with another video. Best of luck with the revision, and I'll talk to you again sometime.